How fuel cells work. One of the biggest problems with a gasoline engine is that a lot of the energy in the gasoline is wasted as heat. Only about 20% of the power available in the gasoline actually makes it to a car's tires. Gasoline engines also create pollution. See how catalytic converters work, page 77. Fuel cell technology is extremely interesting because it can create power more efficiently and with less pollution than can gasoline engines. A fuel cell converts hydrogen and oxygen into electricity and heat. It is sort of like a battery that can be recharged while you are drawing power from it. Instead of recharging using electricity, however, a fuel cell uses hydrogen and oxygen. Like a battery, a fuel cell produces a DC, direct current, voltage. Types of fuel cells. There are several different types of fuel cells, each of which uses a different chemistry. Fuel cells are usually classified by the type of electrolyte they use. Some types of fuel cells show promise for use in power generation plants. Others may be useful for small portable applications or for powering cars. The proton exchange membrane fuel cell, PEMFC, is one of the most promising technologies for small fuel cells. The PEMFC uses one of the simplest reactions of any fuel cell. The basic idea is this. 1. Hydrogen molecules hit a catalyst on one side of the fuel cell. This strips off the electrons, and each hydrogen molecule becomes a hydrogen ion that is missing electrons. On the other side of the fuel cell, oxygen molecules hit a catalyst and each splits into two oxygen atoms. The oxygen atoms attract the hydrogen ions through the membrane and combine. Number 3. Meanwhile, the electrons freed from the hydrogen make their way through a circuit and arrive at the other side of the fuel circuit. Hydrogen ions, oxygen atoms, and electrons combine to form water molecules. The reaction in a single fuel cell produces about 0.7 volts. To get this voltage up to a usable level, many fuel cells must be combined to form a fuel cell stack. Parts of fuel cells. The anode, the negative post of the fuel cell, has several jobs. It conducts the electrons that are freed from the hydrogen molecules so that they can be used in an external circuit. It has channels etched into it that disperse the hydrogen gas equally over the surface of the catalyst. The cathode is the positive post of the fuel cell. The cathode has channels etched into it that distribute the oxygen to the surface of the catalyst. It also conducts electrons back from the external circuit to the catalyst, where they can recombine with the hydrogen ions and oxygen to form water. The electrolyte is the proton exchange membrane. This specially treated material, which looks something like ordinary kitchen plastic wrap, conducts only positively charged ions. The membrane blocks electrons. The catalyst is a special material that facilitates the reaction of oxygen and hydrogen. It is usually made of platinum powder, very thinly coated onto carbon paper or cloth. The catalyst is rough and porous, so that the maximum surface area of platinum can be exposed to the hydrogen or oxygen. Fuel cells use oxygen and hydrogen to produce electricity. The oxygen required for a fuel cell comes from the air. In fact, the PEMFC, ordinary air, is pumped into the cathode. Hydrogen, on the other hand, is difficult to store and distribute. A reformer addresses this problem by turning hydrocarbon fuel or alcohol fuel into hydrogen, which is then fed to the fuel cell. The efficiency of fuel cells. Fuel cells are more efficient than gasoline engines, but they are not perfect. Comparing a fuel cell-powered car to a gasoline engine-powered car and a battery-powered electric car helps us to see the differences. Fuel cell-powered electric car. If the fuel cell is powered with pure hydrogen, it has the potential to be up to 80% efficient. It converts 80% of the energy content of the hydrogen into electrical energy. When you add a reformer to convert methanol to hydrogen, however, the overall efficiency drops to about 30 to 40%. You still need to convert the electrical energy into mechanical work by using a motor inverter with about 80% efficiency. That gives an overall efficiency of about 24 to 32%. Gasoline engine-powered car. All the heat that comes out as exhaust or goes into the radiator is wasted energy. Only about 20% of the energy content of the gasoline is converted into mechanical work. Battery-powered electric car. An electric car has fairly high efficiency. The battery is about 90% efficient. Most batteries generate some heat, but not much. And the electric motor inverter is about 80% efficient. This gives an overall efficiency of about 72%. But this is not the whole story. The electricity used to power the car has to be generated somewhere. If it was generated at a power plant that used a combustion process rather than nuclear, hydroelectric, solar, or wind power, then only about 40% of the fuel required by the power plant converts into electricity. The process of charging the car requires the conversion of AC power to DC power. This process has an efficiency of about 90%. That gives an overall efficiency of 26%. Maybe you are surprised by how close these three technologies are. This example points out the importance of considering the whole system involved, not just the car itself. I'm not going to read the other types of fuel cells.